I'm very curious that how can someone devote 6 years of their life to a particular material? So I'm sure there must have been some story, some incident. What got you hooked onto this material in the first place?
China and Japan built their early bridges using GFRP, just GFRP. Anywhere where there is chances of corrosion, this material was used. Right.
And if we had to fit it,
right,
what would you really suggest? Like, what is the best way to kind of fit it?
If we see the cyclic carbon footprint of steel, to produce 1 ton of steel in its entire life cycle, roughly 2 tons of CO2 is emitted.
That this does not catch rust, this does not catch rust. And I was so curious that how can a material that looks exactly like your steel sections is there and it does not kind of catch rust. Hello and welcome again to the Shine Stars podcast. Today we have an extremely interesting human being with us. And I guarantee you that you would not have come across such a person in your life. At least I have not. So when I first met him and got to know about him, I was so curious to kind of bring it to the rest of the world for you. So let me tell you a little bit about this particular person. His name is Dr. Srujan. And he started off with his career by doing a civil engineering degree from BMS College in Bangalore. After that, he went on to UK and did a master's in structural engineering from Coventry University. And now this is where it gets interesting. After that, he came back and did a degree in law. After that, he went on and did a master's in psychology from Jain University. It doesn't end here. After that was a PhD from Reva University on material science, and his PhD specialization was in fiberglass composites. So the minute we got to know about him, like we were so curious and we wanted to bring him to the rest of the world. And of all these things, the most interesting fact I've not yet said, he did all this by the age of just 26. Can you beat that? Yes, we have a superhuman being with us on the show. Dr. Srujan, so happy to have you here.
Hi, Kunal.
Thank you so much for your time. Like really grateful that you could take time out and share your knowledge with the rest of the world.
That was a wonderful introduction. Even I wasn't expecting something like that. Now that you put everything together, I mean, yeah, it was a one crazy journey that I've come this far. And, I was so glad that I met you because you're working on this one product. Your brand represents this product that I've spent close to around 5 to 6 years researching on. GFRP and FGC, as you guys call it, is a product that I've spent like a good 6 years of my professional life looking into. And I was so glad that I met someone who's manufacturing it in South India. Before this, I was importing all these materials for my research from foreign countries. I'm just so grateful that now I have a source that I can just go walk up to and procure material.
Yeah, thank you so much for that as well, because 6 years of research in the fiberglass composite space, I think when I just heard that, I was like just taken aback, and I've had few interactions with you, and every interaction has been like, I've learned so much out of it. So I really felt that like we should be like quite open and just like go with the flow and share whatever knowledge we can, because in India, it is still kind of catching up. People do not know about it. So extremely grateful that you're with us. So to start off with, I'm very curious that how can someone devote 6 years of their life to a particular material? So I'm sure there must have been some story, some incident. What got you hooked onto this material in the first place?
So I think I should give all the credits to my professor in the UK. He introduced me to this material. So there's this one subject in structural engineering called steel structures, a core subject. So steel structures speaks for itself, right? Deals with steel and all that. So one day he called us into the class and he was like, I'm going to introduce you to something different. And he had 2 sets of I sections in the class. And I was fairly built back then. And he called me onto the dais and he was like, boy, can you pick this up? And me in all my male bravado, I went there, tried to pick it up with a single hand, and I couldn't pick it up. And the professor actually told me to deadlift the thing. And I had to pick it up I had to squat down and then deadlift the thing. On the other side, I see this man just picking up the other eye section with his single hand. And I was mind blown. And this gentleman was in his late 50s. That to me created this point of curiosity. After I kept this thing down, there was that thud sound that came. And when he kept the profile down, there was no sound at all. So my curiosity, as soon as I kept this thing down, I went to pick that up, and it was much, much, much lighter. The next 45 minutes blew my mind completely. He spoke about how this material, which is called GFRP, is stronger than steel in terms of tensile strength, is better in so many structural usage compared to steel, because it is non-conductor of electricity, it's rust-free, does not conduct heat, does not conduct magnetic current, and so on and so forth. The next half an hour I was completely mind blown, and it got me curious. Within the next day or two, I was like, I decided that this is going to be my master's thesis. And I ended up studying so much about this product, so much. The next couple of weeks, I just spent a good 3 to 4 hours with this professor. He was also into doing research on GFRP. And I spent the next 3 to 4 hours just talking to him about the material, because I had collected so much data. And it's not like it's a newly made material. It's been there since ages. It's just that us in the construction industry, we have been so used to using trivial and old school methods that we fail to see the new methods that are coming up and new products that are coming up. So I was fixated. And in fact, that's the day when I decided that not just my master's, I'm actually going to do a PhD in this. Because I knew the potential, the sheer potential of this product. And I knew there were so many lacunas in this space that they can be patentable and converted into a business. So that's how I got into GFRP or FGC.
Wow. Very, very interesting story. So kind of a love at first sight kind of a thing.
Of course. Yeah, sure.
I have a very similar story as well that I'd like to share. So it was during the COVID time, and I was invited to an online event. So there were multiple speakers. So one of the speakers did a presentation on this material, and he was showing photos of this material being used in coastal areas, being used in buildings, and he was saying that this does not catch rust, this does not catch rust. And I was so curious that how can a material that looks exactly like your steel sections is there and it does not kind of catch rust. And so I was like enamored by this material for a good, like a couple of years. It was running in me. I could not like get over it. And when the opportunity presented to kind of like introduce in the market, like we got like really, really excited that can we actually give a viable, credible alternative to steel? So that is the reason why we have kind of introduced it in the same sections. Like if you see a normal steel profile comes in 6 meters, we've also kind of introduced it in 6 meters so that like it's very easy for the end consumer that they do not have to deal with many variables or so. So that was our story. But kind of coming back to this thing, so you did touch upon like while you were sharing that this material has been around for a while.
Yes.
Actually, this is one of the biggest, I would say, the misconceptions that we have had whenever we have spoken about this material is that, oh, this is a new material. So like I don't want to take risk. But I think that's the biggest misconception that this material has been around for quite some time, in fact. So would you like to shed a bit more light about it? Like what is the origin of this material? Why did they invent it in the first place? What was the need for it?
Yeah, right.
And how, like, where is it being used? So a little bit on the history would be really interesting.
So basically, to start with, one thing we have to establish is that this material does not rust. So that was the core principle on why this material was introduced into any field for that matter. Initially, during the early world wars, right, they needed some material that was non-corrosive, because there was so much of steel and metal and, ships, tanks, aircrafts. You said there was metal used everywhere. And the common problem that it had was corrosion. So earlier ideas of inventing a GFRP traces back to around 1930s.
Wow.
Way back.
90 years.
Yes.
Crazy.
But the proper resin, whatever is used in today's date, was manufactured or discovered during the late 40s. So the proper section, GFRP sections, were created anywhere between 1945 to 1950. Post 1950 is when people started developing it even further and started using it in boats, marine engineering, military camps. So basically this material was chiefly used by the armed forces because they were the ones who could afford these things. A common man could not afford these materials because it was very cost ineffective compared to traditional steel. So later, as years progressed, somewhere during 1980s, I suppose, this material was introduced into the construction industry by Japan, USA, and Canada. So, and China. So China and Japan built their early bridges using GFRP. Just GFRP. I think China did it with a composite of GFRP and CFRP. Whereas Japan did a homogeneous bridge built purely out of GFRP. And this was in late 80s. And towards late 90s, somewhere during 95 to 96, everyone hopped on to the trend because the material was non-corrosive. All marine constructions, there were bridges being built, there were decking slabs being made out of this. Anywhere where there is chances of corrosion, this material was used. Also, this material is not as reactive as steel to chemical exposure or radiation exposure. Be it your MRI, X-ray, ultraviolet, UV, material does not react, whereas steel reacts. At the same time, the non-corrosive property helped in marine-based construction or any water exposure construction, be it dams, bridges, culverts. In all these places, in fact, GFRP was chiefly used to make boats because of its lightweight property as well. That's one more thing that I want to touch base on. GFRP material is 4 times lighter than steel. 4 times, right? So the sheer amount of manpower that is required to make a GFRP structure in comparison with steel structure is immaculate because since the material is so light, transportation becomes easy, usability becomes easy, shifting becomes easy, movement of the material from lower level to higher level becomes easy. So it was a no-brainer that this was going to be the next big thing in the market. But, traditional steel industry is so big that people did not deviate towards using this material. And there were certain design code lacunas which are being filled in today's time. If you see ACI, which is American Concrete Institute, they have this one entire module. It's called ACI 440. They have an entire module for GFRP construction. And that's like the holy grail for any GFRP products being used in the construction industry. So, yeah, that's the history of the product. And it's been there since ages. It's just that we haven't introduced it in regular construction because steel was available. Steel had already established its market by then. So people thought, okay, if things are going well, then why move to another product, right? That's the history behind it.
Very, very interesting. So almost 90 years.
Yes.
I think I had also read somewhere, I think in World War II, it was used in helmets, if I'm not wrong. One, of course, that
helmets. So another topic that I would like to talk about is there are various types of FRPs and GFRP is one of those FRPs. Helmets that you speak of, we use something called AFRP.
Okay.
Armored fiber reinforced polymer.
Interesting.
They're also used in Kevlars. Those are the bulletproof vests that our armed forces use. So AFRP is similar to GFRP. The process is the same, but the material being used is different. And we speak about carbon fiber, right? People generally say carbon fiber, carbon fiber. We have CFRP, carbon fiber reinforced polymer. That's the entire thing. So CFRP is like one of the strongest. So we have something called strength to weight ratio. In strength to weight ratio, CFRP packs a number which is 20 times more than steel.
Wow.
Can you imagine?
That's
20
mind-boggling.
times.
Whoa.
It's like out of the world thing,
Yeah.
right?
Yeah.
So, but CFRP is a bit expensive.
Yeah.
AFRP is also expensive.
Yeah.
GFRP is on the budgeted end.
Yeah.
So that's how GFRP was introduced into the construction industry and the various other military agencies.
Yeah. Thanks so much for shedding lights on that. And this is very linked to, as some people would be curious, that why are we calling it as FGC? So that's exactly one of the reasons. So as Dr. Srujan shared, so in the composites industry, there is what is called as an ABCG. So what is the ABCG is A is aramid, what he just shared, B is basalt, C is carbon fiber, and your G is the glass fiber. Because there are so many different types of fibers, like we wanted to be very specific that what we are making is out of glass fiber, and that is the reason why we have kind of named it as Fiberglass Composite. And as Dr. Srujan said, that it's actually not a new material. It's been 90 years there. And even in construction also, it's actually not new. 1980s onwards, as he rightly said, like America, Canada, and Japan has been using it extensively. And what insight you shared is true, that the ACI Institute Codebook 440, that is considered as the Bible.
Correct,
so any structural engineer watching this podcast, all you need to do is like get that code book, the ACI 440. We have it available as well, which we can share with you, where literally it's a 258 page book where everything is listed over here. Like how is it that you can use the GFRP in your one-way slabs, two-way slabs, in your beams, columns. So everything kind of in one place. So that's a good thing that it's been around for a while, and we just need to take the best case practices which have been around. The other thing, of course, I think a very, very important feature of this is the lightweightedness, that it is so like lightweight. So where do you see that this can really make a difference in the construction industry? So any insights on that from your side?
Of course, I mean, GFRP is 4 times lighter than steel, traditional steel. Now this cuts down manpower significantly. This cuts down transport significantly. And all this, end of the day, cumulatively, is reducing the cyclic carbon footprint of GFRP. Now, if you see the cyclic carbon footprint of steel, to produce 1 ton of steel in its entire life cycle, roughly 2 tons of CO2 is emitted.
Wow.
And for GFRP, it's 30 to 60% less. That's a big difference, right? So when we are talking about the lightweightedness of the material, getting into the technical part of things, when we are designing structures, there are various types of loads that we amount to. The common ones being live load and dead load. Dead load is what the structure has on its own, and live load is what goes above the structure or what's on the structure.
Dynamic load.
Dynamic load, variable load, live load. So it's not fixed, it's varying. Let's say, suppose I need to build a building for 100 people. So my 100 people become the live load. And the structure that I'm building becomes the dead load.
Got it.
Okay. So when we are using this material instead of steel, we are curbing down on the weight of the building roughly by 4 times, or the amount of weight that steel is putting is curbed down by 4 times by using GFRP.
But how is it from a layman's angle? How is it good for the building if the dead weight comes down in the building?
You can increase the span from column to column. You can make the structure lighter. You can go higher floors, not worrying about the soil collapsing or going lower. The size of the footings can be reduced because the overall dead load of the building is being reduced. And there are so many other economical and alternative things that can be achieved just by using a lighter profile or a lighter section or a lighter rod. Because you're curbing in a building, let's say the live load is about 60%, the dead load plays 40% in design. So when we are calculating the overall load, right? Plus in India, we use a factor of safety of 1.5. So you multiply that load by 1.5. Traditionally in the UK, when I was practicing design there, we would use a factor of safety of 1.2 to 1.3. But in India, IS code specifies us to use a factor of safety of 1.5. So the buildings that we are building is already so massively reinforced, and the dimensions of columns, beams and slabs are so big that we are pouring in material. These are not economical buildings. To make them economical, we can use this product. You're curbing down, you can make slender structures. Let's say you have a beam dropping down from the ceiling. Would it not look odd? Now to cover that beam dropping down from the ceiling, you're going to use a false ceiling. Now false ceiling adds on to the cost of construction, right? But what if that beam did not have to come down? What if that beam could have been concealed? Such structures are possible using GFRP.
So one of the most frequently asked questions that we get is, in steel you can do welding, but how do you actually fix these profiles?
Yeah, well, to be honest, my thesis is based on connection designs as well. So yeah, I do agree that these things cannot be welded, but they can definitely be bonded. So what weld can achieve on site, you can achieve the same thing with bonds. And these profiles can be manufactured in a certain manner that we don't even have to weld or create a bond for that matter. Now, I chiefly work with pre-engineered buildings, PEBs as we call them. Everything is more or less done in factories and we just assemble it on site, right? So similarly, these structures also can be achieved like that. There's no need for us to break something, cut something, attach, detach and all that. It's like a jigsaw puzzle. You just come and assemble it on site, and that can be achievable using GFRP. Other than that, I think even welding in steel for that matter, the type of welding that's achievable on factories, you can't achieve that on site. Industrial welding, industrial arc welding is completely different from the on-site in situ welding. To achieve that amount of strength on site is not possible. So welding, yes, in very crude way, necessary, but if designed and planned well, we can manufacture the profiles in such a way that they can just come on to the site and we can bolt them up.
Got it. So you also spoke about some bonding. So what kind of bonding agents or adhesives can be used to kind of connect them together?
There are various range of bonding materials. Epoxy resin is the commonly used
Araldite or Fevitite rapid adhesive.
Correct. There are PU based bonding agents and so on and so forth. I've actually tested about 43 different bonding agents.
Wow.
To check with what works well with GFRP. The thing with bonding is to achieve good bonding.
Which were the top ones and the ones that you had researched?
I mean, I had 6 top ones, but end of the day, it boiled down to the mechanism. So now if I were to break down all 6, there are advantages and disadvantages of each type of bond. So the curing time, the bond environment, and the thickness of the applicant all made a big difference. So the basic epoxy resin, what we use for manufacturing these structures as well, they work more homogeneously than using any PU or other based of bonds.
So these epoxy adhesives like Araldite and Fevitite Rapid, they are good because they're epoxy based.
I wouldn't take those brands. There are chemical compositions to it.
Okay. Got it.
Specific chemical compositions to it. It's not brand specific.
Got it. It's more on the
bond specific or chemical agent specific.
Got it. And one more question that we keep getting asked is that to connect the profiles, of course, we can nut and bolt it. But is there an issue if the bolting is done because your nut and bolts are either SS or aluminium,
Correct.
and this is a different material? So would any issue happen when these nuts and bolting is done?
Achieving a composite connection with different types of material being used with our principal material is always difficult. There are challenges in it, and we do have FRP bolts. We don't have them in India, but FRP bolts don't do so well because due to surface abrasion, the bolts tend to shear faster, and they have their own issues, right? And bolt surface has a layer of epoxy in it. So when it comes to abrasion, right, there's a lot of wear and tear in bolts. And GFRP bolts are not so strong in terms of shear. So that's why it's preferable to use stainless steel bolts. After that being said, using the right type of washers, having the right type of bolt tolerance, having the right type of torque in each bolt. Torquing on bolt is a very, very big factor when it comes to the strength of the bolted connection. Can definitely mitigate the failure modes. There are a few standard failure modes: net tension failure, bearing failure, shear out failure, combinational failures. So there are certain types of failures. If we cater to each segment, it's very easy to establish a good bolted structure.
So from again, a common man's perspective, let's say if these profiles were there, let's take this example, and if we had to fit it, what would you really suggest? Like, what is the best way to kind of fit it? And so what would be your suggestion on this?
So I would recommend using a plate reinforcement. So L angles, steel L angles. Now you can achieve these steel L angles, and the design codes are already there. You need to look for it. The thickness of the plate that you're supposed to use, the number of bolts that you're supposed to use. We have something called pitch and edge value when it comes to designing bolted connections. So the distance between the edge of the plate to the center of the bolt, the distance between bolt to bolt, and again so on and so forth. So adjusting plate thickness, pitch edge values, and number of bolts in the bolted connection, a very good strong bolted connection can be established.
Got it. Can we use the fiberglass angles as well? Like, for example, this particular one?
Yes.
Where do they work well with?
They do. Okay. You most definitely can. Okay. One thing that you need to look into is when you're using a composite connection, right? So there are certain precautions that you should take. It might be as small as using the right type of washers or having the right type of tolerance hole. So if the hole that the bolt goes into, if it's too much, then it will obviously lead to more bearing. Bearing is when there is deformation in the bolt hole. So to reduce all that, and even like I said, tightening of the bolt. In technical term, we call it torquing of the bolt. So the tightening of the bolt plays a major factor in the strength of the bolted connection. And the point of failure is chiefly determined by the amount of tightening that you do to the bolt. Too tight, the bolt will shear easily. Too loose, and the bolt will not do its job. There will be a uneven distribution or eccentricity of load flow.
Got it. Again, related to this, a question that we keep getting is that will the threading become loose over a period of time? Let's say if you use an SS bolt and using an FGC angle with this thing. So what's the answer to that? Like, will the threading go loose? Yes or no? If yes, what is the solution? Is riveting a solution, or like your lights on this?
Yeah. So threading, definitely. I mean, if you have moving parts, if there's any dynamic load, if there's vibration, be it steel structure, be it GFRP structure, be it any structure, the bolts are bound to get loose, right? And fastening of bolts is a very common practice from where I stand. Because even when we are building PEB structures, which are purely made up of steel, we make sure that we do our annual maintenance. We make sure that all the bolts are tightened. We make sure that we repaint some of the bolts in places where they're rusted and so on and so forth. So it's no different for GFRP. It's from steel in terms of tightening the bolt.
Is there an advantage by using riveting? Does it have a better grip compared to bolting?
It's not about the grip. Like I said, riveting is a better option compared to bolting. I personally have done an entire paper on how riveting is better than bolting, because in my study, the thing that I observed is bolting increased bearing, increased shear, whereas rivet, because of the smooth surface it provided at the joint interface, the bearing was much lesser. The rivet did not shear out much faster. So there are various advantages of riveting over bolting, but it depends on the quality and the workmanship that the labor has who's doing the riveting.
Got it.
Bolting is a easier process. Any layman can do it.
Got it.
But riveting is a bit more technical.
Got it. Yeah. So the final question on this is that the main interest of everybody for using the profiles is for creating shed works or your pergola structures or all these kind of roofing structures.
Right.
So firstly, what do you see in terms of, is it a good alternative in these applications? Secondly, if it is a good alternative, then like what is the perfect way to kind of go about fixing them?
So GFRP is not just a good alternative, it's a great alternative. So especially in regions where, the entire place is prone to heavy rainfall, fog, mist, humidity, GFRP is one of the best alternative for steel. After that being said, steel also has certain features that cannot be neglected. So based on a technical person giving the appropriate solution to the problem, we need to use that type of material. Where steel has to be used, steel has to be used. Where GFRP has to be used, GFRP has to be used. If not, you'll end up spending more on maintenance, be it either steel or GFRP. You'll end up spending more on retrofitting it when there's any problem. And we already spoke about the rusting and paint peeling off and all that. So, especially in coastal regions and hilly regions, people neglect fog also. People only think of humidity. People neglect fog. Fog is another major factor that leaves a lot of water residue on any surface, right? So wherever you can expect to have these water contacting the structure, it's a no-brainer that instead of using metal, using a particle that does not rust. We spoke about how PVC was an alternative.
Yeah.
So this is also a great alternative.